In the last few videos, we had defined angular variables and torque as a means to simplifying more complicated applications of Newton's laws of motion, which would have to go down to the atom by atom basis. We're going to be continuing that theme here in the next series here, where the trick will be that in certain circumstances, even if the details of how exactly the interaction goes down are either hard or horrendous to calculate, we can find certain quantities that stay the same before and after a process. We call these quantities conserved quantities. And this is actually an application of a rather amazing theorem due to Emmy Noether. She showed that these conservation laws exist because there are fundamental symmetries in nature. So I'll be dropping references to Noether's theorem and the relevant symmetries as we go along. But first, let's start with one of these conserved quantities. This one's called momentum. So momentum is defined to be the product of an object's mass with its velocity. Yes, the symbol for momentum is P. We already used M for mass, don't you know? So the units here typically will be something like kilogram meters per second. And because mass is always a positive quantity, if, say, our velocity is pointing to the right, our momentum would be pointing to the right as well. And since the units of velocity and momentum aren't the same, it didn't matter that I drew the momentum vector longer. I could have drawn it shorter or the same length. It's just that if we've got more than one of these kind of pairs going, they just need to be proportionate. Now, if you go on, eventually when you study Einstein's theory of special relativity, you'll find that we will have to modify this definition of momentum somewhat. There will be another factor called gamma that will also be multiplying this. However, this gamma factor for basically anything in our everyday ordinary life is a number that is only microscopically bigger than 1, and so we'll neglect it here. But if you have objects that are moving at a substantial fraction of the speed of light, just be aware that we'll have to use a more careful definition later. So, just to give a quick feel for this, let's say we have a mass, let's say 0.1 kilograms. Let's say it's moving to the right at 100 meters per second. We can find its momentum. The momentum will be pointing in the same direction as the velocity. It'll be equal to mv. And so the magnitude here would be 0.1 kilograms times 100 meters per second will give us 10 kilogram meters per second. So, but to show that, so here we had a relatively light object that was moving quite quickly, but we could, to have the same momentum, have a rather heavy object that's moving slowly. So here, let's say we have an object that's moving at 0.01 meters per second, but its mass is a metric ton, 1,000 kilograms. It would turn out, in this case, that the momentum is exactly the same. P equals mv. So this would be, 1,000 kilograms times 0.01 meters per second still gives us 10 kilogram meters per second. So both the speed and the mass of the object are at play. And so you could have a small object moving fast have the same momentum as a big object moving slow. So if you remember when we were going over Newton's laws of motion, I gave you the correct form of Newton's second law at that time. And the way Newton wrote it was the alteration of momentum is ever proportional to the motive force impressed and is made in the direction of the straight line in which that force is impressed. So if in modern symbols, the way we would express what Newton wrote in words, so this is the correct version of Newton's second law here, we would write F net equals the time rate of change of the momentum. So another way to put it is what a force being applied on an object does is change the object's momentum. Now, why did we go with F equals ma? Well, F equals ma turns out to be correct in a limited case, but this limited case is incredibly broad. First off, we have to be going at speeds that are substantially less than the speed of light, but that includes basically absolutely everything in our ordinary experience, so that's not a problem. And the only other requirement for F equals ma is that the mass of the thing be equal to a constant. So let's follow through where this goes. So we say F net equals the time rate of change of the momentum of a thing. That would be the time rate of change of the product of the mass times the velocity. But if the mass is a constant, the change in mass times velocity is the same difference as the mass times the change in velocity. Divide by delta t, and we go, oh, hey, that's ma. So the F equals ma form that we've been using all along so far is just fine for most things. Where you do need to be more careful is, like I've said, if things are moving a substantial fraction of the speed of light, but then we would have to use the more careful definition of momentum that we'll be visiting later. But the other possibility is if the mass of the object in question changes significantly. The two classic examples of this are a raindrop falling. In the case of a raindrop falling, as it falls down through the sky, it'll keep colliding with water molecules on the way down. So, and it'll pick up those water molecules. As those water molecules glom on, the mass of the raindrop increases. And so then you have the mass of the thing changing. That means we can't use F equals ma there. And the other classic example is a rocket. Well over 90% of the mass of most, or at least 90% of the mass, in some cases well over 90% of the mass of a rocket, is fuel. It's a very substantial chunk of the mass of the vehicle. And this fuel burns very quickly. So the mass of the rocket changes drastically. Just even within a couple of minutes, you're down to like 15% of what you had to begin with. It's just crazy. So in those cases, you again have to do a more careful treatment where you also have to recognize that the mass is changing. And what you'll get is you'll have an ma term, but you'll also have a term that includes the rate at which the rocket is losing mass. This is why engineers who design rocket motors, in part, try to make the rocket motor burn as rapidly as possible without flat out turning into a bomb and exploding everything. it turns out that you get a little extra oomph for the vehicle if you can burn the fuel quickly. So now where we're going to be going with this is we're going to be re-expressing Newton's second law of motion a little bit. And so to this end, I need to define a quantity called the impulse. It's not something that shows up an awful lot. It shows up just enough that you need to remember that it's there, though. And so we define the impulse of something exerted on something to be sum of forces times times. I'll do this graphically in just a second. But just a quick note, yes, this is a letter J. There's an interesting historical aside on that. It's not J because moment of inertia is a much more important and more widely used quantity, although that's true. It's not J because J is the next letter in the alphabet after I. But actually, if you go back only a couple of centuries, you'll find that a lot of people still kind of thought of J as another way to write the letter I, almost. The sound values of I and J were finishing their divergence in English around about the time this notation started coming down. So it wasn't that it was the next letter J, the next letter after I. That was more like the other letter I, oddly enough. But anyway, let's say we wanted to find the x component of the impulse being exerted on something. What you would need to do is make a plot of the x component of the force being applied onto something as a function of time. Let's say it looks something like this. The impulse is equal to the area under the curve. In this case, this would be the x component of the impulse. Then to get the y component of the impulse, you would do this for the by plotting Fy versus t and so forth. So Jx is the area under the curve for the Fx versus t graph. Jy would be the area under the curve for an Fy versus t graph. So if we map this out, we'll see that the units of this then are going to be newtons times seconds. And it also turns out that a newton times a second is a kilogram meter per second. So it's got the same dimensions as momentum. So newton times seconds equals kilogram. A newton is a kilogram meter per second squared. We're going to times that by seconds. Cancel, cancel. And so we have that newton seconds are the same thing as kilogram meters per second. So now where we're going with this, and I'm glossing over some technical details in the derivation, is we're going to what's called the Impulse-Momentum Theorem. So we start with Newton's second law of motion expressed the way Newton actually said it, that F net equals delta P over delta T. And then for what you do is effectively multiply through by delta T. So this F net delta T, hey, that's the impulse, especially if we add all this up over sufficiently small delta T's. What we get is this thing on the right is the impulse, and then we're left with the change in momentum. So this gets called the Impulse-Momentum Theorem. Now, it'll turn out that it's probably most useful, believe it or not, when the impulse on a system is 0. And in fact, in future videos, you'll see me bending over backwards to create situations where we can make the impulse 0. But there is some direct practical application for this. And this is usually for doing things like trying to characterize the force of a hammer hit situation. So if you think about a hammer hitting a nail, or say a tennis racket hitting a ball, or something like that, what you realize is a couple of things. One, the force being exerted on it changes wildly. If you ever look up slow motion video of a tennis racket hitting a ball, you'll basically see that the webbing almost completely envelops the ball. The ball gets horrendously squished. There are all kinds of crazy things happening. And so the force is not some polite thing. It changes rapidly. And then the other thing is that this rapidly changing force tends to happen over a period of maybe 20 milliseconds or less. So I'll say less than or on the order of. So this is not meters per second, this is milliseconds. Remember, milli means times 10 to the negative 3. So 0.02 seconds. So you're talking 2/100ths of a second here. It's very rapid. And so it can be very hard to measure the forces involved. But let's say you're designing a tennis racket or something like that, and you need to at least have a number that you can hang your hat on to try to come up with some sense of an average force. Well, a sensible way to define an average force for an event like this would be to say it's one that over the same period of application wound up giving me the same impulse. So these areas on a curve would be equal. And then this value right here, whatever height you need here to make these areas equal, would be a reasonable definition of the average force being exerted on something. Now, it may well turn out that sometimes these things get really spiky. So maybe the maximum force is 10 times the average value or something like that. But it would at least give a designer of a tennis racket a number that they can start to work with. They can look at, they can measure the change in momentum of a tennis ball using high-speed video, and they can get a rough idea of the time the racket is in contact with the ball, again by analyzing high-speed video. And from the two of those, they can calculate an average force. And then when they're trying to figure out how, what are the maximum forces that the racket might have to withstand, they would multiply that number by, say, 10, 100, something like that. They would way overbuild it, but at least they have a rough idea, so they don't have to go crazy with overbuilding it. So, as an example here, let's say they measure, in our tennis racket example, they measure that the change in momentum of the tennis ball during a hit was something like 0.1 kilogram meters per second. So we can say, hey, the impulse is equal to the average force times the time of the hit. That's the idea here. And so we can rearrange but the impulse by the Impulse-Momentum Theorem is also equal to the change in momentum that you found. So then you can go ahead and say, well, the average force that the racket was exerting on the ball in this particular scenario was delta P over delta T. So let's say it's 0.1 kilogram meters per second. And let's say it was our 20 milliseconds, something like that. They get that this is 5 newtons. Okay, fine. And that might be an extreme underestimate of what the maximum force would be. So maybe they designed the racket to withstand 500 newtons for whoever this particular user is. But they might not bother to design it, say, to withstand 5 billion newtons. So it's just something that can give an engineer a bit of a number to work with. So that's probably the most useful direct application of impulse. Like I say, most of the time the game will be playing is to create situations where the impulse is 0, and then use the fact that that means that the momentum does not change. But that will be a topic for the next video, so catch you over there.